All right, I think it's recording. All right, and we're gonna start it. Let's go. So, let me start.
Wait.
Oh
Hold
no.
up, Antonio.
Oh no.
Just want to say, if you guys have questions, raise your hand, and I'll like tell Antonio or something, and we'll just raise your hand in the reaction or like type in chat or something.
You're saving my
Okay.
life right now.
All right, bro.
All right. Uh, so many things open. All right, cool. Share the screen. All right. Can you see the screen?
Yes.
All right, thank you. All right, cool. So we're just gonna spend like what, 5 minutes blazing this presentation that we had from the last workshop. This is VHDL part one, uh, brought to you by Lisa Goat. So we're just gonna go over our motivation, reminder, we're learning VHDL, a hardware description language. So the goal is to use the knowledge that we gained from digital logic or online. Instead of dragging and dropping these logic gates, we're going to actually code, and this code is going to be turned into the logic gates that we know and love, right? So then we're targeting an FPGA. VHDL versus Verilog. Verilog is another hardware description language that we'll touch on later. The design structure for a VHDL file, we have an entity, which you can just think of in your head as a black box that has ports that we define what the inputs and the outputs are. And the architecture defines the behavior, how it actually acts, right? The behavior of the black box. Next. Data types and operators, will cover that. Concurrent and sequential statements. So there's a difference between concurrent and sequential statements when we're coding in RTL. RTL standing for register transfer level because we're defining the logic between clocks. That'll make more sense later. Concurrent basically means that it executes simultaneously. So in this bottom one, for example, if there was another line here, they would execute at the same time. Sequential means one after the other, right? So in this process, typically how like normal programming languages go, like Python and C++, they happen one after the other. So this if statement would be if this, then, and go to the next line. And if that's not true, go to the next line, etc., right? We'll cover these now, and then I just added this slide as like a buffer. This is what you guys came for, right? This is me. This is the Apply Online guy. So what I wanted to do was make these combinational circuits in front of you, explain what they are, and then do them. And I also have test benches so we can see like what's actually going on. And for some people who haven't taken digital logic yet, or like in the process of learning it, what I did was like I have the picture of the circuit, what it's supposed to look like. I have the truth table, which a truth table is just basically all the possible combination input combinations of the circuit. That's what the output is supposed to be. And you can describe this as like smaller gates. So like the fundamental building blocks of what we like. And gate here, or gate here, not gate here. So this is a 2-to-1 mux. These gates are what's inside this pretty much. So I first wanted to start with a multiplexer, and I'm going to stop sharing my screen because I just showed you what a multiplexer is. If I find where Zoom is, it's over. We're going to turn to Visual Studio Code. So if you want to follow along, open VS Code, start a VHD file, and then we'll get going. Let me pull up what I was doing because I forgot. Let's do this. All right. So now we're going to be going over to the mux. All right, I'm going to share my screen one more time. Courtesy of Dr. Stitt, I have all of these architectures and entities. I'm just going to explain what they are line by line. So as you guys remember from the first part, we have these two lines, which are pretty much like header files. Can you guys see my screen? I forgot to ask that. We cool?
Mm-hmm.
I bet. So these are like header files. This is in particular, or yeah, in particular standard logic. That's what we're using to define what our signals are. Library IEEE, that's where this is, right? Then we're defining our entity. Remember, entity is like defining the input and output port, right? So what we're going to do, we're going to specify port, semicolon. Inside here, we define each one of our signals. So let's say in order to match what we saw from the 2-to-1 mux, we had two inputs, which were in 0 and in 1. We had another input select, because remember, depending on what the select value is, in 0 or in 1 get passed to the output. Then we have output. So that's like our input and output port, right? So we're going to do this. In defining in 0 as an input, standard logic defining this is the type of signal that we're defining it as. And in standard logic, that can be 0, 1, don't care, unknown, and uninitialized, right? So that doesn't matter for now. I think for now, for like learning purposes, it could be a 0 or a 1. The rest we'll see in simulation when you build up to even more complex circuits, which is the whole point. This is the whole point. Then we have output. This is our port, and we are done. So now we have to go to the architecture, right? I have a bunch of different architectures. A reminder that in VHDL you can have different ones. And when you go to put it on your FPGA, you can choose which one you want to synthesize to. So the reason why there's a lot of them is because we want to show you the different types of like conditionals and stuff that we have in VHDL. You've probably seen in Python, C++ if you are familiar with those. So let's start off with the first synthesis guideline for combinational logic. All inputs should be in sensitivity list. Let's break down what that means, right? So we have a process because I want to run the if statement sequentially, one after the other, right? So I'm going to write this if statement. And then VHDL's weird syntax, if then, else, and if. Just gotta be there. Gotta know it. In this process, inside this parentheses is what's called the sensitivity list. Basically, what that means is any signals that are in the sensitivity list, once they change a value, like say in 0 goes from 0 to 1, then this process block is run. If it goes back from 1 then to 0, this process would run again. And we can see in simulation, if we like don't include all the inputs, then it won't behave like we want. For example, the behavior of a mux, right? If select is 0, it chooses in 0, and if select is 1, it chooses in 1. But if we didn't include select in the process sensitivity list, then it would never run when select is changed, and that'd be a problem. So we're going to include in 0, in 1, and select, because those are 3 inputs that we have, right? Then we have to describe the behavior that I just said, right? So if select equals 0, what do we want to the output? That was not me. We want in 0 to go to the output, right? So we assign output with the value of in 0. And this is the assignment operator in VHDL, caret equals. Else, which means if select is not 0, so assuming it's 1, since the only other value it can be, output is in 1. And we are done. You just made a mux. Oh my God, get a job. Let's go. I'm going to breeze through these pretty fast because this is the general behavior of a 2-to-1 mux. Am I missing anything? I think we're cool. I don't know, it's telling me an error. I will keep going. So then the case statement. So instead of using an if statement, we're going to use a case statement. We're just going to copy paste this stuff in here. I wish it was tabbed. There we go. All right. I'm going to get rid of the if statement. I'm using a case now. Case very similar to if you've seen in C++ or Python or C++. We define our case. It autofill for me. Oops. We have to see what the value of select is. So that's what we're doing here. We're into the case. Then we do when select is a certain value, let's say 0, for example. Then we define output to be in 0, like we were specifying before. And then this other cool thing that VHDL has is others. So it's just basically saying when there's another, when select is whatever else, in one gets passed. Good. And then when else, this is just one line. Output equals in 0 when select equals 0. And if not, equals in 1. Notice that we have this not inside a process because it's just one line. We could put it in a process, but it'd behave the same way. And then for the with select, which is the last one, output equal to in 0 when select is 0, in 1 when others. And that's it. This is basically just saying, hey, we have a bunch of these architectures. Which one do we actually want to put on our board? And so you can pretty much instantiate which specific architecture you want. So for this case, we're just going to synthesize the if statement one. So we're going to ignore the rest and just go back to the if statement. I wonder why it's throwing an error, but we'll see, I guess. I don't know. All right. If you were following along, this is what we're doing in Model Sim, Open Model Sim. If you're not following along, you want to do this later, I'm going to post all the test benches. So is assuming that you follow the synthesis guidelines, you should have no errors on your test bench. So we're going to add the file that we just finished plus the test bench. I think it's in here. These two, right? Okay. We're going to compile all of them. Yes, it works. So we created a new project in ModelSim. Then we added the two files, the one we just coded and the test bench that will be provided. We compiled them. We would see down here if there was any errors. There's none, right? The next step is to simulate. We want to see how our circuit actually behaves and if it's in accordance with how we want it to behave, right? So I clicked simulate. I went into the work folder and I'm selecting Mux 2-to-1 test bench. That's what I named my test bench. This is like a lot at first glance, but if you want to keep at it, it'll be cool. And it'll be less daunting when we do. So what we're going to do first is we're going to select the specific architecture that we're simulating. We're going to drag all of the I/O. Where's the button? And then we're going to click, where is it? This one. It says run all. We're going to run all the tests. For some reason, output's undefined, so I'm cooked. I save this. Maybe that's why. I just saved in VS Code, which means that it'll update here, so I don't have to recompile. So we're just gonna compile all of them again. There's an error, no! Near process expecting begin. No, you serious? So we gotta go back. Oh, it's missing a begin in the architecture. There we go. That's it. Oh, it's out here. All right, that was it. So we saved it, which means it's gonna be a question mark again, right? Assuming. Hello. Whatever. Okay, so now it recompiled. Now it's saying zero errors. We're gonna click simulate. We're gonna click restart. So it restarts everything, right? Then we have the IO that we defined, right? Click run all, and it's all green. Once you are able to create your own test benches and stuff, you can write stuff like simulation complete, which means you're at the end, obviously. But in case you run into an error, then you can see like, oh, if you catch this error, right, like, oh, this test did not work. So now we're just gonna go over like one case to see if this is working, right? So if select is one, we want to select in one, right? So if in one is, well, let's go right here. In zero and in one are both zero right now, but select is one. So that means output should pass in zero, which it does. Or in one, which it does. In one and output match. So that means it works. Let's go here. Let's just click select and click find next transition. That just means the next time select changes in value, right? So like if we were here, click here, that's when it's one. We're gonna click one more time. Select is zero, and in one is one. Select passes in zero to the output, which is consistent with what we want, right? And then if we decided to go down here and change which one we're actually instantiating, say we wanted to do the case statement, that means that ignore all the architectures except for this one. We're expecting it to behave exactly the same. So we're just gonna go back to model sim, right click, compile all, no errors, let's go. We're going to restart our simulation. And then now that we're using a different architecture, we need to replace the IO, right? So where is that thing? Oh wait, there it is. Okay, so we're gonna click the specific one that we're using, specific architecture. We're gonna drag and drop these, run all, and it works still. Simulation complete. If there was an error, it would say it down here, according to the test bench. So now that we're done with that, we're gonna move on to the next thing, which is priority encoder. So I couldn't find like a really good representation of like what it is in terms of like the small scale logic gates like and or and stuff. So I just didn't. I couldn't find one for the multiplexer either, but it's easy to like write it out. So I just drew it. But for the priority encoder, I attached a playlist if you guys are interested, or maybe some people haven't taken digital logic. This is NESA Academy's digital electronics playlist. So like if you want a refresher on what these circuits do, or if you haven't taken digital logic yet, this is a good place to like learn before taking digital logic, I guess. Similar to the mux that we had, this is the truth table, and this is what the priority encoder looks like. As you can see, the way a priority encoder works is, let's say we have a 4-bit input. In this case, it's called I3, I2, I1, I0, right? Whichever one is asserted, like say 1, the highest one, that will get passed to the output. So if we look at I3, since I3 is asserted, we don't care what the other three are. Y1 and Y0 will pass 3, which is 1, 1 in binary, or I3. And then same thing with I2. If I2 is 1 and I3 is 0, then it'll pass 1, 0, etc. So let's go back to the code. Uh, we're gonna make a 4-input priority encoder. I know I'm going a little bit fast, but keep in mind there is an IEEE event at like 7, and I don't want to conflict with that, and also it's recorded. So I hope people that are following along, if you get confused, you can ask questions at the end maybe, or watch it back. So the way we're doing this now, I forgot to delete the port. Inputs, standard logic vector, 3 down to 0. So this is a little bit different than we did for the mux. Our mux was in standard logic. You're probably asking, what the heck is standard logic vector? It's a vector. Come on now, bro. So this specific syntax, you can describe a bus. So in the mux 2 to 1, these were just 1 bit. It could be 0 or 1. But these are 4 bits, 3 down to 0. 4 bits being like 0, 0, 0, 0, 0, 0, 0, 1, etc., right? And we specify in this parentheses what we want it to be. So if we code it like this, 3 down to 0, it would be 3, 2, 1, 0, where 3 is the most significant bit. You could also do 0, 2, 3, where 0 would be your most significant bit. But in order to be consistent with like how we were taught and like the best, it's just the standard to go most significant bit is the highest number, right? This valid bit is just making sure like when we get our result, is it valid, yes or no? When valid is true, that means that we can trust that our result is the right one. And then our output is called result, and it'll be 1 down to 0, so it'll be 2 bits. So now we're going to do the first architecture, which is the if statement. I might not go through all these because I want to make sure we have time for the rest. I think I'm just going to go over the first one because I think you understand. So we're going to start with how we did before with the mux process. And in order to capture the behavior of the priority encoder, I'm just going to remind you, if I3 is asserted, if it's 1, we don't care what the other ones are, right? So if we're thinking about like an if statement, it has some sort of priority depending on what you write first, right? So if I do an if statement where, let's say we're looking at the third bit or the fourth bit in this case of inputs, so the most significant bit equals to 1, and say for like the next one, like else if inputs 2 equals 1, if we put inputs 3 equals 1 first, this is the first thing that it will check as soon as the process is run. So just take a note of that like an if statement has some sort of priority depending on how you write it, right? Then I'm going to write the rest of the skeleton for this. Also noting that whenever we are checking if it's asserted, we have to put it in quotes. Also looking at this, this is so weird. Else if, but it's not else if and it's not elif. What is going on? That's VHDL, bro. And then the last one, else. And then we end the if. All right, so remembering our truth table, if inputs 3 is asserted, we want the result to output 3, right? So we're just going to do result. We're going to assign it with 1, 1. Notice how we have 2 quotes now because this is more than 1 bit, right? For 1 bit, we can use 1 quote, but anything more than that, you need double quote. And since this result is valid, we're also going to assert valid. If inputs 2 equals 1, so now if this was not true, it'll pass on to the next if statement, right? That's how if statements work. So that means that inputs 3 is not 1. So now we can just type what it should equal if this is the most significant bit that's asserted. If inputs 2 equals 1, the result should be 1, 0. We also want to assert that our valid equals 1 as well. All right. If inputs 1 equals 1, we want the result to be, nope, to be 0, 0. And valid equal to 1. in order to like show you the the purpose of the valid bit, what we're doing is if inputs 1 equals 1, then it's 0, 0. We could have done 0, 1, but let's just say that if inputs 1 is asserted, this result is 0, 0 and valid is 1. For any other case that we didn't cover here, like say input 0 is asserted, or like none of inputs 3, 2, or 1 are asserted, we're going to say that the input is 0, 0. But now you don't know if you don't know if this is true or this state is true, which is why we have the valid bit. So now you know if valid is ever not 0, it'll be because inputs 3, 2, and 1 were not asserted. And we are done. I think doing the second if statement is pretty beneficial because it's like the same thing, but it's just one thing to note. Let's see, what I forget. Yeah, that's it. All right. Just gonna copy paste this to the second architecture. We're using this second just to tell you that since we have to assert valid, notice how they're asserted all the time. This leads us to our second synthesis guideline. Define outputs on all paths. I should have explained this a little bit more. When I say synthesis coding guideline, we're writing these circuits, right? But we have the goal in mind to put this on an FPGA. So when I'm saying synthesis, we are synthesizing our code to be put on the FPGA. There are some circuits that aren't natively on the FPGA, and I'm basically singling out a latch, which is if you have taken digital logic, you know, or you can look up from the Nesso Academy, YouTube, whatever. It's not like a circuit that's like on the board. It's not like a resource. So it can cause unexpected behavior, etc. I'm not doing it justice with the explanation, but the reason why this is important is because if you define your outputs on all paths, you won't create a latch. If you don't define your outputs, you'll create a latch, and then it'll like the combinational logic, which you want to have like no memory, will have to remember the previous input because you didn't define it everywhere. And that's
May I
not
chime
good.
in?
I bet.
Another thing is that you can write code in, let's say, VHDL system Verilog that is not synthesizable but still usable for test benches. So you can simulate certain behaviors, such as, oh, if you want to like divide in your test bench, um, it can do that in the code, but only in simulation, but it actually doesn't synthesize onto a board. So it's useful for like replicating certain behavior purely in simulation for the sake of making like a golden model when you're testing.
That was really good. So for the test bench, you brought up a good point. You don't have to make the test bench synthesizable. Once we get to like a test bench workshop, you'll understand like how to make a test bench and stuff. But we just want to see if our circuit is working. So we don't need to worry about putting it on the board. Just need to make sure we replicate the behavior. Anyways, back to this, right? So I assign valid everywhere, but what if outside of the if statement, I just asserted valid equals true here? It'd be true in every single path here. And any case that gets to this else statement, valid will be 0, and these two architectures are equivalent. So if we go back to model sim, did I save that? I did not save it. All right, we go back to model sim, click end simulation. What we're gonna do now that we moved on from the Mux 2-to-1 example, I'm gonna right click, add to project, existing file. I'm gonna look at where I made the priority encoder. I'm gonna include the test bench. Going to right click here. I'm gonna press compile all. Unknown expanded name. I'm so cooked. All right, I gotta open it. Default. Oh, I gotta make sure it's the same one. Yeah, it's the same one. Might just recompile again, see what happens. All right, there we go. Sometimes that happens, bro. Gotta work through it. All right. Went too fast here. Simulate. Start simulation. Going into the work folder, which is where all of our stuff is. I'm gonna select priority encoder test bench. Where is it? There we go. Okay. We're gonna do what we did before. We're gonna find our port, inputs valid result, drag it over here, click this called toggle leaf name so we can see what the actual names are, right? We're gonna click run all, and it's gonna run. Awesome. Let's go over this real quick. Let's find a test case here that we can talk about. Let's see when valid is true. There we go. All right. 0, 0, 1, 0. So if we look at our priority encoder, we do 0, 0, 1, 0. The one that's asserted is inputs 1. So it should be here. The result should be 0 and valid should be 1. So if we go to our model sim at the time that this is asserted, valid is 1, which is what we want here, and result is 0, which is what we want. Pretty good, huh? The next thing we're doing is an adder. So there are a bunch of ways to make an adder. There are a bunch of adder architectures. We're just going to talk about the full adder. So what we're doing is we're just adding A plus B like I did here, this miraculous drawing. I looked up adder and this came up. That was pretty funny. We're also taking into account C in and C out, carry in and carry out. In case there's an overflow, we account for that in this full adder. So,
Can I chime in again?
say it again?
Can I chime in again?
Yeah.
You can think of this full ladder example as A plus B plus C in,
There you go.
if the C in kind of made no sense.
You're right. Thank you. Thank you. Hold on, I'm eating.
You gotta focus on the work, man.
Feel the flame. Okay. We have library IEEE, standard logic, which what we've seen before. You have to include those before every entity in order for that to apply to the entity, right? That's why it goes before this add entity, right? You notice this third one, numeric standard. In order to perform like arithmetic operations, this package is really nice. You can also look it up online and it'll show you the operations that it has. But for this specific adder, I'm going to be using this and only this. There's also other packages that you can use to make an adder, but we're not doing that. Generic. I did not explain this before, but this is what's called a parameter, right? We're naming the parameter width. So we can basically define a signal that has width size. And this number gets specified in the test bench. So basically we can do it, we can put any number that we want. If we want this adder to be 3 bits long, we would say width is 3. And in this port here, it would do 3 minus 1 down to 0, which is 2 down to 0. 2, 1, 0. That would be 3. That would be size 3, right? Then there's other parameters here, or there's other types that width can be. But for this case, we're going to do positive. Positive, if I remember correctly, is anything from 0 and on, or might be 1 and on. And there's other ones that include negative numbers, but we're just going to do positive, right? Input 0, input 1, sum, carry out. That is our port. So I wanted to, this might be like the bulk of the workshop just because I wanted to do like a bad architecture versus a good architecture. And so we can like debug what's going on in model sim, right? So let's start with our process. Synthesis coding guideline 1 was include all the inputs in the sensitivity list, right? We do in 0 and 1 begin. Let's go. What happens if we want to interpret our input values as signed or unsigned? We need to specify that. If you guys recall from digital logic, or if you guys have covered like binary addition and subtraction, if you're familiar with 2's complement, sometimes when you interpret, or not sometimes, when you interpret a binary value as signed, the most significant bit, if it's 0 or 1, determines the sign of it. If it's 0, then it's a positive value, and if it's 1, it's negative. So in order to make an unsigned adder, which is the goal, we have to cast these inputs to be unsigned. So what we're going to do is sum equals, we're going to cast it to unsigned in 0 plus unsigned in 1. And we're done. So along with casting these to unsigned, we have to make sure that they're the same width as our sum, right? If, let's say, in 0 and in 1 were their max value, and we added them to sum, it would exceed this value. So we have to make sure that we take that into account. So now I'm going to introduce a signal. A signal is like a temporary variable that you can use inside your architecture, which is why it's defined in the middle between architecture and begin, because the scope is limited to the architecture. We're going to write signal. We're going to assign it a temp. That's what we're going to name it. It's going to be unsigned, and it's going to be width down to 0. So this is of type unsigned, and notice it's one size bigger than the inputs and the sum. So instead of doing this, what we're going to do is we're going to assign temp to this, right? So now in case these two are their max values, temp will be able to take care of that because it's 1 bit bigger than the inputs and the outputs, right? But we also have to resize the inputs as the same width as temp. So this is one thing that might be a little tedious in VHDL, but all signals have to be the same width in order for you to add them or do arithmetic operations on them. So we're going to do the resize function. There's a second parameter here, which is what do you want to resize it to? We're going to resize it to width plus 1. I did that in the wrong area. Oops. Oh, width plus 1. Here we go. And then we assign sum to temp. Notice how it's giving an error. We have to make sure that we're assigning, not only do they have to be the same size, they have to be the same type. So we notice here temp is unsigned, sum is not. Sum is of type standard logic vector. So in order to assign it, we have to cast it to standard logic vector. And then on top of this, temp is width down to 0, sum is width minus 1 down to 0. So we also have to cast it back to width minus 1 back to 0. So we can splice it. We're just going to grab from temp, we're going to grab the width minus 1 down to 0 part. This carry out, noticing it, or it's telling us if there is a carry. Let's say input 0 and input 1 were max again, they would just like overflow, but you couldn't tell unless you had a carry out signal telling you that it was, right? We're going to define carry out to be the most significant bit of width, or of temp. And that should be it. And you'll notice why it doesn't work in simulation. You're going to save, go back to model sim, do the whole thing again, end simulation. All right, we're back here in our project. Right click, compile, or right click, add to project. Existing file, we're gonna click the things we just worked on. Add, wait, in here. Add and add test bench, these two. Want to compile them? I gotta double check to see which we set to. Oh wait, it's here. We're gonna show off the bad architecture first. So I have to save that in VS Code, go back to model sim. It's gonna show the question mark. We don't know what it is. Recompile again, compile all. You can also select just one and compile selected. I'll compile that one. Compile out of date, ones that were added that aren't compiled yet. But in case you have like a really, really big design, and if you click compile all, it'll take like a super long time, like an hour or something, you can just compile selected. But since these are really small, I just click compile all the time. We're gonna click simulate. Start simulation. Work. Find our adder test bench, click OK. We're gonna select these. Oh, did not mean to do that. Notice how width in this case is 8. That's because in our test bench, we defined it to be 8. So now in 0, in 1, and some, anything that was defined with that width parameter now has like a set size. We're going to delete width because we don't really need it. Click assertion violation. So that's what I was talking about when I was saying like you can write whatever you want in your test bench. Okay, I didn't mean to click that. That's crazy. So it's saying we have an assertion violation at this time. We can actually click on the error and it'll take us to when that error was made. So in the test bench, if the tests are not running as we want them to, we can write those errors. Then one other thing we can do in Model Sim, in order to make this look easier on the eyes, we're going to change the radix. Let's just do unsigned because that's what our adder is, right? It's throwing us an error and wherever I clicked, I don't remember. 71 plus 157. If we use a calc, which is short for calculator, by the way, you have 71 plus 157, boom, 228. But right now it's showing 227. Why is that? Well, let's see sum 227. Let's go to the next iteration. 158 plus 71. So we're seeing that in this specific part of the test bench, this in 0 is staying the same, and this in 1 is incrementing by 1. But if we add 71 plus 158, it'll be 229, not 228. And that'll be consistent with this entire thing because the way we coded our adder, it's off by 1. So this brings us to the next architecture, which is the good architecture, which is the same thing that we did here. So I'm just going to copy paste. The one difference being a signal updates at the end of a process. So in this original architecture that we had, temp would not be assigned this until it gets run the next time, which is why in the simulation it was lagging. One thing that we can do to change this is instead of making a signal, we can make a variable instead. The big difference between a variable and a signal, well, two things. Variable gets updated immediately, so that's like the answer, right? But also, it's limited to the scope of a process, which is why in this first one, the signal we put between architecture and begin, and this one we put it between the process and begin. So you can only use this variable inside of this specific process. We're going to write variable temp, same thing as before, unsigned, width down to 0. Boom. One other thing to note when assigning values for variables and signals, variable is the one that has a colon equals. So there's a lot of like really weird syntax when it comes to this stuff, but the more you work at it, the better, the easier it'll be. So now that we fixed that, we're going to right click this one, compile selected. adder was successful. I forgot actually. We have to go down here and define that the one we're working with is the good one. We were looking at good one. Did I save that? I'm so cooked. Save. There we go. Compile selected. Successful. Simulate. Restart. Okay. Test completed. We didn't get any errors at all because the temp is not lagging by 1 anymore. Because the variable updates as soon as it's asserted, right? There was one other one I was going to do. Or was I not? Oh, here it is. There are other ways to do this with like concatenation and stuff, but I don't want to go over that because we're kind of pressed on time. I just wanted to do, let's do good 5, which is basically just these again. Good 5. Since temp is not a variable anymore, we're just going to do caret equals now. I think that's it. Oh, define as a signal. So now that we're using temp as a signal again, you're going to expect it to not work, but this highlights the difference between concurrent and sequential statements really well. As a refresher, concurrent means they all happen at the same time. Sequential means one after the other. And in a process, all of them are sequential. They happen one after the other. But since we're out of a process, in our case, I clicked the wrong button. We got to restart the simulation. Look back at the code. Right. These are outside of a process. So all of these will happen at exactly the same time, which is what we want for a combinational circuit. So if we click this, test completed. We have no errors. Now moving on to what's the next one? A multiplier, A times B. I didn't check to see if this was right. I didn't check the truth table, whatever, but we're just gonna like do it. You can look at that on your own time if you are interested. We're gonna go over how to make a multiplier, and I'm gonna call it after that. So there are a bunch of ways of implementing a multiplier, but I think I'm just gonna show, I don't even know. We'll see what we get to. So now we have our input width, which is one of the parameters that we set. We have is signed, which is a Boolean, right? Could be 0 or 1. Then we have our port. Is signed is going to tell us, do we want to sign or do we want to multiply signed numbers or unsigned numbers? So if obviously if is signed is asserted, if it's 1, we want to multiply signed numbers. We have to interpret the in 0 and in 1 as signed. And if it's not, then they're unsigned, right? So then in 0 and in 1, standard, you've seen them before. Input width minus 1 down to 0. Product now has to be double the size of the inputs. So you can just do input width times 2. That takes care of the port. Now let's get to the first architecture. Let me see. Yeah, we're doing arch1. Where was I? We're going to make a process because this is combinational logic. Include in 0 and in 1 in our sensitivity list. Go to our process. First, we have to check to see the signs of the inputs, right? So if is signed. If is signed is true, right? If is signed is true, all we have to do is assign the product. We have to multiply in 0 times in 1. Does that numeric standard? It does. And then we have to remember from what we did in our adder, first we have to cast these to either signed or unsigned. So since they are signed, we're going to cast them to signed here. inputs here. And then since these two are signed, the result of multiplying them is going to be signed too, but the product is standard logic vector. So we have to cast the whole thing to standard logic vector. That's it. But if it's unsigned, we do the same thing, but we put unsigned instead. It works. So let's just go to model sim. We're going to end simulation. We're going to add the ones we just worked on, mult and mult test bench. Compile out of date. So the ones that aren't compiled, right? I'm just going to recompile again. Okay. I love when it does that stuff. It's my favorite. We're going to select the test bench. Also, one thing that I want to note, I'm going to end simulation. Anytime we're using model sim, this is really important. When we go click simulate, start simulation, once we find the thing we're looking for, we always select the test bench. Because in model sim, we're like driving the inputs to our DUT or UUT through our test bench. DUT stands for design under test. Unit or UUT is like the same thing, but it's just a different terminology, unit under test. And it's referring to the specific circuit that we made, the one that we were coding just now. So let's just add these. I think that should be good, right? Test completed. Let's go. So let's change these to decimal, I guess, because we have signed and unsigned, right? So let's just go to like a random, like let's go here. So pull out the trusty calc again, voucher for calculator. 102 times 81 is 8,262. And since it's a signed value, it'll be negative because we have a negative sign in front of the N1. But if it's unsigned, let's see, let's go back to, oh, actually, let's just change this to unsigned. Assuming that both of these are unsigned, 102 shouldn't change, right? Yeah. Unsigned, negative 81. Unsigned is 175. So now we have to do 102 times 175. Our answer should be 17,850, and it is. So our multiplier is working as intended, which is good. I'm gonna move on to multi-low. So this is a new entity that we're starting, right? So we have to include these again, defining a new entity multi-low. This should have the same functionality as before, but instead of one single product, it's going to divide them into a high and low signal. So these will be the same size as the inputs, but this one will have the high part of it and this one will have the low part of it. The reason why we're doing this is so we can see how to splice into the signals, right? So we're going to define arch1 and we're going to do, let's see, we're going to comment all of this out. I did not mean to do that. And then we're going to uncomment all of this. All right, that's tough. Trying to do control minus, but it didn't work. All right, so we're going to put these up. We're looking at this one, the one that we're making right now. Arch1, here it is. So we're going to do the same thing we did before. Just going to try to speed up here. We have the if statement that we had before. Ugh. Okay. So in order to like splice into this result, we have to first store the result somewhere, right? So we're just going to use a temporary variable. Variable temp. And this should be the same size as the original product was, which was input width times 2 minus 1 down to 0. So now this can hold the full product. So if sign is true, I don't want to write this again. I'm just going to copy paste. We're assigning temp with the result. We have to change the name of, it used to be product, and then the assignment operator because this is a variable. If it's not true, these should be unsigned. And we're done. So, and colon equals. Now that we have the actual result, like the full result, we want to assign high and low. We can do this outside of the if statement and by splicing into temp. So since temp has both the high and the low that we're looking for, we're going to splice into temp by adding the highest, the most significant bit, width times 2 minus 1. And we're going to go to input width, which is exactly halfway down. And for low, below, we're going to splice into temp with the next bit, which is input width minus 1 into 0. Come on now. There we go. So that should be good. So we spliced temp. This is the top half of temp, the highest half, and this is the lowest half. And we're assigning it to high and low, and we should be done. So we're going to go back to model sim. Do this one last time. That's not what I want to do. We're going to compile. Let's compile selected. Successful, no errors. Restart the simulation because we just compiled something. We just changed something. Okay. Hello. Where'd everything go? What's going on? All right. We're gonna do molt test bench. All right, come on now. All right, I'm gonna restart awesome. I don't know. Maybe I did something in the wrong order or whatever, but whatever. Okay. Round 2. Oh my, it's bugging. It's bugging so bad. There we go. All right. Make sure everything compiles correctly. Simulate. Start simulation in the work folder. Molt test bench. Let's go. Noting that, where is it? We're instantiating arch1, which is the one we just did. So this should reflect the behavior, right? Test completed, which means that we didn't run into any errors, which means that it should be good. I'm wondering where, did I grab everything? Where's high and low? We should be seeing high and low. I don't know. Well, high, low, arch1. All right, I might be cooked here. I don't remember. Should be good.
What's the issue you're having right now?
We just finished making arch1 for molt high, low.
Okay.
I just checked to see that this is the one we're trying to test, yes. And then I went to model sim and it's not appearing at all. It's kind of strange.
Did you restart simulation?
Yeah, I did.
And go to the project. Let me see if you recompile. Weird.
Y'all are just gonna have to trust me.
Trust the process.
Trust the process.
Bad teacher, bad teacher.
So cooked. Oh
Hey,
well.
it's okay.
I've hit a snag, but I think we've covered what we covered here. Gonna go on to the next one, which is an ALU. Just want to say that ALU, if for people that don't know, is one of the labs for digital design. In my opinion, it's pretty good at being like a starter circuit to, hey, I know what I'm doing in terms of combinational logic, which is what we covered today. So you can look up what an ALU does. It stands for Arithmetic Logic Unit. I should have wrote that on the slide. But it is one of the things that are in CPUs, Central Processing Unit, which you guys definitely know about in computers, because computers are so cool. We're on a computer right now. So it's too long to do here. Left as an exercise to the reader. And the test bench will be provided in case people want to actually do it. Then you can have the test bench run the workflow that I just showed you today in ModelSim to see if it works or you get thrown errors. This is the entity or the entity that you want to follow. So in 0, in 1, select neg, pause, 0, output. And then I'll tell you what each one does here, right? So for the select, which is 2 bits, when select is 0, 0, you want to add. So you want to add input 0 and input 1. For 0, 1, you want to subtract input 0 and input 1. For 1, 0, you want to AND input 0 and input 1. And then finally, for when select is 1, 1, you want to OR them. The neg, pause, and 0 are negative, positive, and 0 flags. Whenever a number is negative, like say that you're adding something, if remember how we were talking about 2's complement, if the most significant bit is 1, that means that the number is negative. So maybe you can check if the most significant bit of the result is 1. Then you would assert your negative flag to be true. Same thing goes for positive, and if the result is ever 0, you assert 0 as well. And that's it for like the functionality for the ALU. If you want to work on it, feel free to talk on the Discord to other people. Maybe you're having like issues in ModelSim that you don't understand. That's why we have a Discord, because Discord's the best. And that should be it. Thank you for coming. If you were following along, I hope it made sense. If you didn't understand something, I hope that my explanations were good enough to where if you go back to the recording and listen to it one more time, it's cool. But if you have any questions, or maybe I didn't explain something well, let me know. Critique me, because if I eat, we eat. We just gotta build each other up. That's what the point of the mask is, bro. So good job, guys.
I love us.
Thank you.
I love
Any
Thank you.
us.
questions? Anybody have any questions regarding anything?
No, you're goaded.
Okay, bet.
All right. Peace
I
out,
love
brother.
us. I
All
love
right, I'm gonna
us.
stop sharing and I'm gonna stop the recording.
See
Thank
ya.
you for everyone who came.